Yeah, welcome back to Cloud Computing and Big Data. We have now part 2 of our lecture 6, being about deep learning driven by big data. And in order to understand deep learning here with convolutional neural networks, which the second part entails, we started in the first part of this lecture a little bit like making the connection from a linear learning model, what we had in earlier lectures, let's say the perceptron learning model, which means linear learning model because it's linear in weights that we learn, up to the idea of using cutting edge artificial neural networks, two hidden layers maybe for small application problems like MNIST, and have seen that this raises somehow the accuracy bar. However, we have also seen that by doing so, we have still, let's say, several drawbacks. And one of them was, for instance, vectorizing. We have to reshape the input to a 1D problem. And that means the information that is sort of hidden in the, let's say, neighborhood of 2D. And we will see now in the second part, also the neighborhood of 3D, will be something which is, of course, an important problem or let's say challenge for those networks where deep learning is really thriving as one of the concrete examples. And then another one would be also the number of hidden layers that we also want to understand, because deep learning, as the name suggests, deep in the sense of many, many hidden layers, is also something that we have carefully to review. So fasten your seatbelt to a, let's say, quick dive into deep learning on a very specific type of, let's say, model, the convolutional neural networks. But let us review a bit what, generally deep learning is all about before we then come to these ideas. And then also how it basically reflects ideas we had towards our MNIST problem. I start with the impact of deep learning. As I was alluding to before, in my research group, we have numerous applications these days on transformer models, and other areas like autoencoders, for instance. These are all cutting edge deep learning algorithms. We do some trainings there on YouTube, basically, if you want to know more. In the IAAS project, for instance, from me, where I have just then really 2 hours just for one AI model, one transformer model, which is really cutting edge these days. There are also other topics like hyperparameter optimization. And today we will, in the second part, learn a little bit more why hyperparameters are crucial in machine learning. They already learned a little bit with the learning rate, another one or one form of a hyperparameter. This can be also loaded for SGD, right, to find the local minimum. But still, setting these hyperparameters is something where a systematic idea using RayTune, for instance, for tuning might be very useful. And then distributed deep learning, I put that here as well, because in a way you would say what we learned now is, okay, we have smaller ANNs, we have smaller CNNs, and you will see, okay, maybe one GPU is enough. The real, let's say, interesting effect for big data, especially, which is part of the course, is enabled through distributed deep learning when you really use not one GPU, but maybe 512 GPUs in parallel. We do this in the research here in teaching. Every now and then we boil down the problem, of course, to making it accessible for 50 people at the same time. But still, take away the message that deep learning, what we initially maybe when it was starting thought as a hoax. I remember talking with some of my colleagues here in the faculty and saying, well, that could be quite a hoax as deep learning. Now it has really stood the test of time in very different areas, also those which are quite, let's say, non-intuitive for these deep learning models, like this, for instance, fluid gas dynamics is an area called computational fluid dynamics, very much driven by physical models based on known numerical laws of physics that you will use iteratively. So here, machine learning has proven also to be quite competitive in protein folding, similar elements, and also even in gaming. So, I mean, many of you have basically heard, I think, from AlphaFold, which was one of the breakthroughs really of deep learning, again, beating a human player who is a champion on this. So, and wherever you go, mostly for vision, natural speech recognition, very much of these traditional computer vision problems and natural language processing is now basically or has been shown that deep learning has quite a significant impact. And of course, for all of them, there's some orthogonal message why this is part of a cloud course like this and the big data course like this. They all are fueled by big data, and they all need significant computing power from HPC or cloud computing. Hence, We had the idea of talking in earlier lectures already about this graph, so I don't go into this detail. I just augmented a little bit. Again, remember, big data, that's where now your traditional algorithms from scikit-learn, Weka, Octave, MATLAB will end, because you have not memory enough and also not computing capacity enough to break through all of this big data. But still, traditional learning models, when you have not much data, can make a big difference, right? So this is standing for this area. As soon as you start with medium deep learning networks, large deep learning networks, you're really in a much more higher accuracy, but you really need to have big data for it. And what you also see is then when you come here, zooming in, the training time footprint, right? This standing, of course, for the idea of how much computing is needed, how much data is needed to be computed. And the more you dive on in large deep learning networks, like autoencoders I was alluding to, transformer models and so on, I mentioned before, you have an enormous accuracy, but you have to have the data for it. And of course, also the computation complexity is not to be underestimated. So for all of this, it's quite interesting to know that these three gentlemen here got, so to speak, the Nobel Prize that we have in computing. It's not really a Nobel Prize, it's a Turing Award in 2018 for the, let's say, reinvention, if you want, of deep learning, because the concepts have been there a little bit before, long time before, where these gentlemen also contributed, but you never had the computing capacity. Now, with the advent of GPUs, with the advent of cloud computing, high performance computing, you basically, first time in history, in the last, let's say, almost 10 years maybe now, you get more and more to the grade of that you can compute these algorithms. And that is, of course, a very important part. However, this graph suggests a little bit a too simple idea of saying, well, then just give me the biggest computer and give me the largest deep learning network and I learn everything. Right. So this is also, I want to quickly give you a contrast statement where here you see an idea of Ray's, how it was analyzing this, that when you ask 4 GPUs to solve a problem up to 2048, it's true, it really, the speed up, it goes much more quicker, but you will see after a certain idea, it will significantly drop in terms of efficiency. And this has to do with the problem of large batch sizes. There will be also accuracy and training error. So we talk about here. Of course, in a way, it's good to add more GPUs, but this is not a concept that will last forever. These are more the details then. That, of course, this comes on then to maybe thinking about that you need this hyperparameter optimizations, how many layers are really needed, and so on. Hence, this slide is a bit simplifying all of that, bringing all of that together, computing, big data, and machine learning, deep learning. But of course, the devil is in the detail for the different applications. Also, a kind of misconception often is the idea that deep learning stands for deep, just adding more neurons and neurons. And this is the graphic that you have here in part 1 of the lecture. We had this nicely 2 hidden layers. We added and everything was nice. It was 95% performance. So the idea is now thinking in your head, just adding 2 more hidden layers, or maybe 20, and then I go to 100% performance, right? And it's not the case. So again, when you think about deep learning, the idea is in a way having more layers, but usually, and also here today, really in a concrete example with convolutional neural networks that you see a little bit indicated here, you come to an idea which is much more smarter than just adding layers of these neurons, right? Which maybe eventually leads to overfitting and so on. Here you see different elements we will discuss in detail in this lecture, but take away the message that even parts of this deep learning network are responsible for extracting features automatically out of your data. I put that conceptually a bit here, where you would say in traditional times, before deep learning existed really, what some of my, let's say, early PhDs have done, right? They did data, they did feature engineering, feature transformations and so on to get good features to learn from machine learning. And this is, sort of speak, the traditional machine learning model. For instance, putting the neighborhood into the picture, as I was saying, right? So there are several aspects. One of my students, first PhD student, basically was doing nothing else than feature engineering, thinking about how you could, in a tree-wise fashion, aid the neighboring pixels in that basically come from Earth orbiting satellite data. But this is now the interesting thing which changes a bit with deep learning. It has a certain feature learning aspect. So that, as you see here, some parts of the deep learning network, and this is just the example of CNNs, you see autoencoders have another interesting idea as well, how to learn features. And we cannot go into autoencoders or in transformer models and so on, all in this course. Otherwise, it would be a machine learning course. But still, the idea is to learn these features more or less a bit more automatic. And with this, maybe more efficient than humans could do. Still, one part of the network didn't change. For instance, when you want to do this MNIST character recognition, the 3 should be coming out at the 3. You need some classification layer as well, based on these features that are automatically learned. Hence, there are similarities, and you would see the softmax function that we learned in the earlier function giving probabilities of the classes still remain. But what is added are basically smart layers to work on the data. And a little bit, this video I showed earlier already in classes should demonstrate this. I would like to replay this a little bit, just because it so nicely captures the essence of this different steps we have been going through at the beginning of the course with linear learning models, ending now up to the so-called CNN I want to show you a little bit more. So here we are back to the initial parts of the course with a perceptron learning model, just one layer essentially, or not even a layer, just a perceptron connected to the output, which was then just basically giving us a probability what digit it is. But it was already the multi-output perceptron, right? We have a multi-class problem here. Now the multi-layer perceptron, which some people also call artificial neural networks, we had now in the part 1, right? Where you clearly see here the structure of the different layers, hidden layer, output layer, and then putting a probability over it, what's coming out of the signals, giving us a probability which class it maybe entails. How many neurons I have really in these layers is something, of course, what you steer. One hyperparameter you have to have in your hands, and also determines the accuracy of this. And now we come to the topic I will introduce you. You will see everything is a bit more complex. We have still different layers, but the layers, as I was suggesting to, have a specific function to carve out features, right? You see that a little bit in this interesting feature maps that you see here. So they try to analyze what is, what different 3s have features in. So is there something common I can analyze? And this will be the common theme throughout this today. So you see it's not anymore just layer by layer and have then 20 layers, but they do a certain specific way of analyzing this. The spiking neural networks is a little bit more alluding to future ideas how to do this. I think that is a bit out of scope here today. Just take away the message that this idea of convolutional neural networks, of learning features, breaking them down in smaller and smaller chunks, can also then have enormous impact of elements which features are basically not completely shown maybe as a whole picture, like you see here, right? So for face recognition, you would say, well, I want to analyze that this is a face, but because you boil it down to different features like nose, ears, eyes, and so on, it's easier for the network to then recognize this is probably essentially a picture of a human. And that's sort of, let's say, the something like in higher level perspective, how that really works. You break it down into the smallest bits and pieces, even so small that some of the networks we learn, just learn basic principles like corners, edges, black, white, and so on. But of course, bringing them together creates an eye, creates a nose, creates an ear. And getting those features together then again gives you these interesting faces. And with this also something we call location independency, what I will go to in a moment. So in order to understand this then, let's break into some details. Again, convolutional networks usually would entail a complete lecture, and then there are different variants of it. So we will go a bit quicker here on it. but in a way, it has a very nice concept, looking a little bit like a human on the problem, right? And again, if we would say we have our 28 by 28 pixel image, we have the same inputs, the MNIST data set you already know, and we will go basically as a human kind of systematically over it, right? We would say this here is a sliding window or a window where we go over it and try to analyze basically what is in the picture. And if you think about a cow, for instance, we recognize a cow by having an interesting pattern between, you know, black and white or brown and white or so. So you move over the picture as a human and try again, similar like the CNN, actually to find features that then means, oh, this is not a zebra, apparently, this is a cow, because a zebra has another pattern, another set of features. So, and you can go on. It's really something that a little bit is alluding to how, you know, the vision in human works. And you basically can indicate it like here, this 5x5 local connectivity, as I put you, in an automatic fashion now, putting that into computers from the human eye. You would say you connect it to the next layer by moving with this window of input pixels through the picture and identify something you actually realize. This is, of course, a hyperparameter. No one tells you that 5x5 is a good value, right? So this 5x5 convolution alluding to here. But this is something what you also can steer. How that then works is that you can, in a way, get this input through this so-called filter, which you also compute mathematically and then have a convolved feature out of the image. You see that a little bit how it works here by going through this filter that you put over the data set. You kind of come, of course, to an output which is smaller, which includes then this convolved feature that you're searching for. And you continue with this. First thin layer, input neurons, first thin layer, next neuron. You can see that you then reduce also the data side, making it a bit more compressed, but also enables you to get, you know, different features learned from these interesting filters we apply. Hence, this is one of the successes of thinking now that I can learn elements from going systematically, like this visualization as well, through the pictures with certain weights that I learn, right? Creating certain feature maps. Again, here the the notation of the weights are important. Think about this. These are all now basically not anymore 2D. This is here even in 3D elements, suggesting that there's an RGB picture, for instance, right? Red, green, blue. The different channels basically that exist in an image. You put different weights to it to come to a filter and then basically thinking that you have a feature map, which is then the convolution. And this will be done many times. So you can steer the amount of feature maps. And this is an application domain problem. You have to steer it yourself as a configuration option. But this is also then how much you can steer of whenever you detect the feature. This should be firing, so to speak, when you do inference. So you're training this, of course, adjusting these weights, more precise. And when you put it on inference with a new image, these basically should fire as a signal. These identified, let's say, feature maps or the signal. Of course, more in the neuron speech, this would be all looking like this. There are still several neurons with all different weights that is indicated by this. So here's a very simplified notion of how it goes through all the different layers. But again, as I was saying to you also, the neural networks and the deep learning networks have a sort of a bit of difference, that they have several dedicated layers for learning features and so on. And one of the ideas is what we have seen already here with a convoluted feature, that you put this also through a nonlinear activation function like the red-defined linear unit we have seen. That is very similar to the idea that we have seen also through the perceptrons. So this remains as an idea. But then you have a new layer that is performing, for instance, pooling. There are different pooling layers available. Max pooling is often used. It stands a little bit for the maximum strength of signal survives, indicating that the signal should fire, of course, when there's a maximum strength, identifying some feature map, for instance, or some elements of a feature maps, like part of an eye or something like this. So you see that by iteratively constructing it like this, you would say the input is a car here as an example. You have this convolution rectified linear unit with different feature maps that will be created. You still pool them. So you really make them more dense, more smaller, and then you start the whole process again with convolution, learning different smaller features perhaps, until you come to another pooling, stronger signal survive, and so on and so on and so on. Now, the interesting thing that I was also alluding to in the MNIST example, the end of the story is that you still have, preserved the local proximity while learning the features. But when you want to fire them up, basically, and to understand in terms of classification what it is now, you still flatten it and have this dense connection at the end with a softmax probability still, although we're talking about a deep learning network here. So this is a part that sort of is very similar than the one we have seen in the artificial neural network world. But what it adds here to be really successful in deep learning is to learn the, let's say, features of a car itself, right? So having, tires, having front lights, having et cetera, et cetera. And this enables us very sophisticated applications. And of course, we come back to this in lecture 7. Again, 1/2 of a lecture is barely enough. And the way how that works is now something I put you here, a very nice live demo. I usually don't do live demos in the conceptual lectures like today, but I think this is an example where you should all basically explore a little because it's quite impressive and it really helps a lot in the understanding. And this is here an idea of, for instance, doing 2D convolutional network visualization, where you can actually have a very interactive way of working with this. So you would have the different layers we talked about, the different feature maps we defined. And then here we have the dense layers at the end that flatten and dense then towards the output probabilities. Hence, what this is showing is that, for instance, with the 8 that you pay, actually here an interesting touch of your visualization skills will remain in different 8s. Right, and you see here again the connectivity, right? When I go through all of this, that of course, in a neural network fashion, that is more and more omitted these days in deep learning, because it's clear for people that, of course, here the neurons are interconnected, like here, like we have seen in the neural network visualization, right? We still have these weights to learn, yeah, that you see here, basically. But people omit them because now we talk about very, very, very many of those. Right? Again, think about what we talked about, this sliding window. Each of this neuron is with a sliding window here connected to the other image before, making it more sort of a feature max already here. Then we have some pooling going on. And you see here the downsampling pooling layer, right? That we can hide, show to get an understanding. So here you see a little bit, it is still essentially the same feature idea, but I really condense it with a pooling in this area, and then I form again a convolution on all of these that I had before here, and come then and later on to this 2 fully connected layers here that you see at the end I was alluding to, then giving us certain probabilities fully densely connected. That means also here every one of these is connected to everyone else in the next layer, so that we have a certain probability here that this is hopefully an 8. So from the probability, you see also a second guess, right? And that brings us back to the softmax that is here and computing probabilities. Some things and some features can be, if it's maybe at the end of the day and you do the same and look at this at 12 o'clock and you're tired, you would say, oh, that could be almost a 0. So there would be some features firing where you would say, this is an exact feature. Now think about how a 0 would like, right? You would share certain elements here which are the same like an 8. Hence, you have seen the first guess, which was before the 8, was basically the second guess a 0. And now when we paint a 0, it's pretty obvious here something may be missing in the beginning, but there's a certain probability of features, right, that are shooting here, basically the round thing here, that there's also, this could be part of an 8, right, when I do this. And with this, you could say it's also badly formed 6, where I just didn't stop here. So making as a second guess a 6. Hence, deep learning and machine learning overall is rarely really giving you always 100% performance. And I will come to that in a moment. So I'll leave it at this. You can play around with this tool, which we actually can nicely quote from this gentleman, Adam Hurley here. I think it's an exceptional contribution to the field, especially in learning how that looks like. A very intuitive interpretation how you could really learn this. And the different models here, 3D fully connected network visualization, different dimensions and so on. So I would encourage you to check a little bit and play with this in your time. So by having done this a little bit, I guess the intuitive notion of how it works is a little bit obvious to you more and more. The same as here on the slide, right? A 7. If you basically craft this a little bit, let's say in a different fashion, you could say, almost say it's a 3, right? Missing maybe the medium or the thing in the middle. And think about that these networks now learn a 7 that is maybe written by over 10,000 people, right? Think about the MNIST data set. We want to come back now. We have 60,000 training examples we want to look at. It's the same data set, right? Nothing changes here. We have the same data set I was alluding to in the beginning. Some of them is training, some of them are test. But it's not only you that writes a 7, there are many others that write a 7, and they all write them differently. Hence, the network tries from all these different examples to learn a kind of interesting feature approach, how 7s maybe look like, and then condenses information through subsequent pooling of saying what is maybe a small part of a 7 that we could always fire, not knowing if it's actually a 7 or a 3, but it could be a 3 or a 7. It is the same feature in a way. And through this concept of breaking it in this feature learning, this enables us also more applications, like using these pre-trained networks, so to speak, for transfer learning, which is an important hot topic in the research, where you use maybe something you use for image recognition at large, maybe between, recognizing it's a truck, it's a cow, and so on, I was alluding to earlier, maybe using this pre-trained features and then fine-tune on, let's say, a particular set of cars. So what can we learn to differentiate between a Ford or Renault or Ferrari? So these are elements in transfer learning, and admittedly that would be again 2 or 3 lectures in a machine learning course, very important today. Also, if you think about a so-called term called foundational models, which are incredibly used in research these days, all what we cannot go into, where I have to refer you to a proper machine learning course. But it's a very exciting field, and several of the concepts you see here really gave rise to it. When we now implement this and want to also, of course, contrast it with performance to our previous models, we see that the model of the sequential remains, but now instead of having this whole idea of reshaping, of basically put it all in one large vector, we don't have to do this really anymore, right? So compared to the ANN with 2 hidden layers we had before, we take the whole signal, the whole input image, and actually putting it then in a 2D convolutional level. We have a certain kernel size going over it, creating then this feature maps, and padding reflects to something that if the picture doesn't really has such, let's say, size that the kernel can properly always go, from the stride perspective, so going 2 to the right, 2 to the right, etc., then you maybe lose some features, or you basically come to a position where there's nothing in the picture left, which makes a kernel of 5 happening. So in other words, if it doesn't fit, you would use some padding. You can see here the pooling idea of how you really now do the max pooling size of going through over the data set. Here you have a 2x2 pool size and a stride of 2x2 going through this data set here, and create a, let's say, very dense representation instead of before. But as we were alluding to earlier, that's not where we stop. We have another completely convolutional layer again, creating even more feature maps, right? So this is something, of course, what you steer with 2050 here as an example. Another hyperparameter where nobody tells you that this is exactly like this. So you can play around with this and would say, well, maybe 30 feature maps give us a better accuracy than just learning 20 feature maps. And this is again alluding to this hyperparameter optimization. However, on the element that I also talked to you before is now think about that there's rectified linear units are there, there's interesting activation function which are non-linear. And at the end, what you would do is then this aspect here, you will flatten everything still now in one layer, but you have learned features in a 2-dimensional sense. Right now is the time to break them down into one vector, because I want to have another dense network given an input to the softmax layer we already know. That gives us then a probability from 0 to basically 9 of all the characters that I want to analyze, so 10 classes of what I should maybe report. You have still very similar elements, right? You have the number of classes, optimizer to choose from. All what you do is basically have a much more smarter way now to analyze your input, going through it successfully, not just by training weights, by also having some interesting features like pooling on convolution operations. So by doing so, another view to see that is a model summary, very nice function that shows you again the number of parameters that needs to be learned, right? Remember these connections. It looks like beautiful here because you omit most of them. The interactive demo, that's one reason why I show it, has still, of course, you fully interconnect through all of these. However, there's a certain amount of weight sharing going on, which is also an important concept, where basically you don't have a dense network completely anymore, but you share the weights to recognize features. So basically having still lots of connections, but less as you would in a dense layer, where every neuron would be connected to the other neuron and so on, like happens in the dense layer, or what we had in the artificial neural network that we called shallow learning, because we just have actually used 2 layers. Here you can add also more layers, right? Here's just 2 convolution layers, several pooling layers, then a dense layer. So that already give rise to the term a little bit of deep learning. And in this sense, you have to pay the price for it. As you know, when I always talk about it, we have now 1.2 million parameters. Thank you very much. And this is entering a category of elements which you would explore also doing your assignment yourself, where CPUs are at the end, right? So basically we see here a nice move, not only from, let's say, the flexibility of a network, so how you steer it, how you configure it. We talk about deep learning architectures, right, that you really create depending on your problem at hand. We see here also the idea that this has an enormous impact, firstly, on the amount of data you need to train all of these parameters. It's actually called also, learning theory, if you want, so the probability of learning. You need a certain amount of data really to learn so many data, so many parameters. That is really coming back to Hoeffding's inequality, the law of large numbers, so really core of machine learning theory, that you need a certain number of training samples to really learn in a proper fashion these amount of parameters. Hence, the requirement for big data, right? If you go to these, let's say, deep learning networks and with so many parameters, and you would have, instead of, let's say, MNIST 60,000, you would have 100 and 100, chances are that this network will not perform very well. Having 60,000 for such a trivial problem, right? So we think about a 10-class problem, very simple. Also, the data set is well preserved. Also, we have a supervised learning problem here, giving us even layers, giving us even labels, what it is, so 10, 0, 9, and so on, from all of these 10 classes. This makes it a bit more simpler. But this is really now standing for a massive requirement of big data and also a massive requirement of computing, because each of these weights that you want to train now here, the trainable parameters, is of course something where we try to use the optimization techniques we have had before in the smaller, let's say, neural networks. But here we do it now on steroids on very many interconnects and all of these different, basically mostly omitted connections here, right? But take away the method with weight sharing, they're still digestible, and all of these dense layers here will contribute to all of these trainable parameters. Hence, using it, this was just a function. The way how you use it is very similar still. You use a number of epochs, how often you go through the data, how many data samples you put in one of those batches to go through. The optimizer could be Adam, could be stochastic gradient descent. Adam has sometimes some advantages over the typical SGD because it takes a velocity in one respect, it's called momentum. So quickly you went downhill before, a sort of momentum going downhill and so on. So a bit more advanced optimizer, but it doesn't matter. It still captures the idea of finding the lowest error rate. And here is something which is already alluding to something I want to show you in the video. Also, regularization, validation are important concepts in machine learning I can't teach because I don't have time. We want to learn a little bit more about clouds and not completely machine learning. But the experts in machine learning are basically really need to require the understanding of validation and the understanding for regularization. Validation for model selection and introduce a certain bias in the data. Hence, here's a certain split of the data for it. And these are all advanced concepts that you normally have to understand, and which makes the model also better in the end, reporting to something out of sample that you basically have seen in one of my earlier lectures. And the way how we use it is now, of course, very similar, the training and test. We still have the idea of normalizing, but we don't reshape, right? If you remember. So this is an important factor now, that we use as the training and the test images more or less as is. But of course, here we use them a bit for mathematical convenience, again, normalized, because in the end, it's all mathematical operations. So again, this was a sort of introduction to deep learning, and admittedly, we left out several different concepts that you otherwise would really go into. And there's lots of hidden assets basically on this. But you see here, when you use this example, for instance, that you also try to reproduce in assignment 2, we see essentially a 99% performance. And this is extremely good in machine learning, if not the best in the end, because some of you would argue, well, such a trivial problem from 0 to 9 recognition, why is that not 100%? Right? We add just 100 feature maps and 50 feature maps in the beginning, maybe one more layer. This must be doable. But think about that, we are reproducing how we learn, in a way, the humans learn, right, with a neural network idea. And you can admit that on the right-hand side, you see here some examples that basically in this data set, when you go through it, you don't really know what it is, right? So this is standing for the large class of machine learning problems as a whole, that there will be always some samples which have some noisy, as we call that, noise inherent, some noisy feature parts, where you don't really know, was this now sort of by the guy that wrote it or lady a 2? Was this a 2? Or maybe it was just the start of a 9. So you will be in doubt. And by this, if you put it to new unseen data, there will be never 100%, because also the network can be never sure if this will be basically a 1, or did you start it maybe with the features of having a 7. You just basically the kind of ink dried out when you wanted to fulfill it to a 7. And these are concrete examples now standing for large class of machine learning. Again, you should be really careful when someone is reporting 100% performance. 99 is already excellent in the field of machine learning. I would say even more or less rather for toy problems. More realistic would be 80 or 70%, right? In a real, let's say, use case in where you don't have all the data perfectly annotated, where you don't have all the labels perfectly. So 99% performance is really because this is a test data set, a very trivial problem, and you have lots of data combined here, and also a nice test set. Hence, we achieved 99.36%. Again, here in the Jupyter Notebook, how that looks like, I think that's no news. But here we also see the requirement now when you would use Google Collaboratory, for instance, to really use GPUs instead of CPUs, because you will explore that executing a convolutional neural network with all of these interesting features we have seen of connecting the layers and the feature maps and so on are just beautiful for GPUs, but a CPU is not having the same performance. And this is also part of assignment 2. I will allude to a later lecture. I will give out assignment 2 next week, and then we can talk about it. We still have to have some conceptual footprints of deep learning first, what we will introduce also on Tuesday, right? When we think a bit more on the clouds, this was now a bit more the general understanding of deep neural networks. And in the last couple of minutes, I would just like to give you this video here as an idea that really you have to think about topics like regularization that combat overfitting together with validation. And this is really required if you want to be, let's say, an expert in the field. And many of the hints I have here in the lecture might be also very good. Among them is, of course, the most important one with the visualization of these different layers I was alluding to. I would encourage you to all look at this. So I will say we see us in the next lecture.